Hi there, in this video I'm going to discuss the double angle formulae. So here goes. So let me title this double angle formulae. And let's take a red pen and a ruler, underline this. So let me write down the double angle formulae. So in general, so there's one for sine, one for cos, and one for tan. So number one, sine 2a, that is 2 sine a cos a. Okay. Number two, cos 2a. So cos 2a is cos squared a minus sine squared a. Okay. Now, using the fundamental Pythagorean identity, you can get two more versions for cos 2a. Okay, so let me explain. So remember the fundamental Pythagorean identity. Let me use a red pen. So since cos squared a plus sine squared a is equal to 1, okay, if I rearrange for cos squared a, so if I rearrange for cos squared a is 1 minus sine squared a. Okay? And if I replace cos squared a here by 1 minus sine squared a, you can get another expression, another identity form for cos 2a. So if I replace the cos squared a by 1 minus sine squared, I'm going to have 1 minus sine squared a minus another sine squared a. Okay, so I'm simply replace cos squared a by 1 minus sine squared a. And if I were to simplify this, I'll have 1 minus 2 sine squared a. Okay. Now, if I use the same fundamental Pythagorean identity, so cos squared a plus sine squared a is equal to 1. And now in this case, if I rearrange for sine squared a, so if I rearrange this identity for sine squared a, it's 1 minus cos squared a. Now if I go back to cos 2a is equal to cos squared a minus sine squared a, and now if I replaced sine squared a by 1 minus cos squared a, let's see what we're going to have. So cos 2a is equal to, okay, cos squared a minus, and if I replace the sine squared a by 1 minus cos squared a, and if I simplify this, so cos squared a minus of a minus cos squared a means 2 cos squared a. So cos squared a minus into minus is a plus. So cos squared a plus cos squared a is 2 cos squared a minus 1. Okay, so cos 2a, in other words, is either cos squared a minus sine squared a, so I'll call that number 1, or 1 minus 2 sine squared a, let's call this number 2, or 2 cos squared a minus 1, let's call this number 3. Okay, and let me call this double angle formulae number 3. There's one for tan 2a. Tan 2a is 2 tan a divided by 1 minus tan squared a. Okay, so let me take a red pen. Let's highlight the double angle formulae. Now, where do they come from? The double angle formulae, you can get that from the compound angle formulae. So in a previous video, I explained the compound angle formulae, and I explained some examples of 2 instances whereby the compound angle formula can be applied. So if you haven't seen that video, I'd encourage you to watch it. But to get the double angle formulae, what you simply do is replace the b by a. So if you replace the b by a, and if you use the form sine A plus A, sine A plus A, if you replace B by A, is sine 2A, and sine 2A will be sine A cos A plus cos A sine A. Okay, so sine A cos A plus cos A sine A will give you 2 sine A cos A, the first double angle formula for sine. Okay, doing the same for cos, so if you replace B by A, and if you use the form cos A plus A, cos A plus A is cos A, okay, minus sine A sine A. Cos A is cos squared A minus sine A sine squared A. That gives you the fundamental form for the double angle formula for cos. Okay, and you do the same for tan also. So that is where the double angle formulae come from. They originate from the compound angle formulae. Okay, now let me give you a tip in terms of when to use the double angle formulae. So here's a tip. You mainly use the formulae, so this often works. Okay, so this often works, so this mainly works. Use the double angle formulae if your equation contains 2 of an angle. Okay, so let me just make a tip and let me write it out in shortened form. So if your equation contains, okay, so this is contains. So if your equation contains 2 of an angle, so for example sine 2A or a cos 2A or a tan 2A, okay, so the 2 of the angle, so I'm using A as my angle, that indicates you may need to use the double angle formulae to help you solve the trigonometric equation in question. Okay, so that means may need to apply double angle formulae. Okay, so let me take this forward with some examples. So let me continue on the reverse. So let me show you what I mean by this. So example number 1, let's underline this. So example number 1 is to solve the following equations, and the range, so the range for angles x lie between 360 degrees and 0 degrees inclusive, and let me call this part A. So we need to solve cos 2x is equal to sin x. So let me show you how this is done. So remember my tip, if your equation contains 2 of an angle, you may need to use the double angle formulae to help you solve that equation. Okay, so this mainly works. Okay, so if I look at my equation in question, I have a 2x, so let me highlight that in red. So I'm going to be using one of the double angle formulae versions for cos 2x, okay, to help me solve this equation. So if I go back to my double angle formulae, the one specifically for cos, now cos 2a is either cos squared a minus sine squared a, so I labelled that number 1, or 1 minus 2 sine squared a, I labelled that number 2, or 2 cos squared a minus 1, labelled number 3. So if we go back to the question, ideally, if we can create an equation involving sine, okay, we can solve that equation and eventually work out all of the angles x between 360 and 0 degrees. Okay, so if we choose the version involving sine, so if we go back it's going to be number 2. So number 2 is cos 2a is 1 minus 2 sine squared a. Okay? So let's use that version. Let me call that step number 1. So step number 1 is, let me make a note, we're going to be using cos 2x, that's equal to 1 minus 2 sine squared x. Okay? And if I replace the cos 2x by 1 minus sine squared x in my equation, I'm going to have on the left 1 minus 2 sine squared x, and that's equal to sine x on the right. Okay, so the idea of doing this is, remember, ideally it's easier to have an equation involving one term only, but to be more specific, it's easy to have an equation involving the smallest power term. So the smallest power term is sine x. So if we can make everything in terms of sine, that will help us in order to work out the solutions for x for this question. Okay? So now if I rearrange this, let's see what we get. Okay? So if we rearrange this, if I bring all of my terms to one side, so if I take the minus 2 sine squared x and the plus 1 to the right hand side, we're going to have 2 sine squared x plus sine x minus 1 is equal to 0. Okay, so in this case, let me call that step number 1. So here's step number 2. Okay, so step number 1 is to create your quadratic. Okay, and in step number 2, I usually let t equal sine x. So if I let t equal sine x, my quadratic will be of the form 2t squared plus t minus 1 is equal to 0. Okay, you don't need to do this step. Okay, so you don't need to do this step. You can solve using this quadratic involving sine, but this for me makes it easier for me to recognize and solve. Okay, so I usually do this, and by working out the t values, I go back to the substitution to work out the x angles later on. So in some cases, some people will like to replace the trigonometric ratio by letter to make the equation easier to understand and follow. Other people will prefer not to do this and solve this quadratic involving the trigonometric ratio. So either way is good. Okay, so in this case we can factorize or use the quadratic formula. So if we factorize, the two factors will be 2t minus 1 and t plus 1. That's equal to 0. So you have two values of t, so either 2t minus 1 is equal to 0, which means that t is 1 over 2 or half, or t plus 1 is equal to 0, meaning that t is minus 1. Okay, so this takes us to the next step. Let me call this step number 3. So in step number 3, I have my t values. I'm going to replace them into the substitution that I've used to work out the two equations that I need to solve. So since t equals sine x, so the first t value is half. So when t is equal to half, that implies sine x is equal to half. So I'll call that equation number 1. Okay, so we'll solve that very soon. And I have another one, another t value. So when t is equal to minus 1, when I replace in my substitution, sine x is equal to minus 1. Let me call that equation number 2. So we have two equations to solve, and for each equation we need to work out the x angles between 0 and 360 inclusive. Okay? First things first, let me solve equation 1. So, brand new page I think. So, equation number 1 reads sine x is equal to half. So, we have a plus half, so sine is positive. That gives us an indication in terms of where to plot our principal value. So x, the principal angle, inverse sine of half, and that is a standard result. That should give you 30 degrees. Okay, so in this case, let's plot that 30-degree angle where sine is positive. Okay, so I think a cast diagram is in order. Let's include some quadrants. So in this case, let's label the quadrants A, S, T and C. So we need to plot 30 degrees where sine is positive. So sine is positive in the first and second quadrants. And remember, angles are measured from the horizontal when plotting your diagram. So 30 degrees in quadrant number 1 from the horizontal, a rough indication here in quadrant number 1, and 30 degrees in the second quadrant from the horizontal, a rough representation, this angle here. Okay. Solutions, on the other hand, are measured from this initial line, and since we're looking at positive solutions for x, between 0 and 360 included, positive angles are measured from the initial line here in the anti-clockwise direction. So in the anti-clockwise direction until we hit that first line, I'll call the first solution x1, that is 30 degrees. Okay. The next solution, I'll name that x2. So from the initial line until we hit that second line here, that is 180, the angle in a straight line, minus 30 degrees. Okay, so that is 150 degrees. So all in all, we've got two solutions for equation 1, sine x equals half. But don't forget, we have another equation, number 2, sine x is minus 1. So let's solve that equation. So here is number 2. Sine x is equal to minus 1. So the minus 1 indicates sine is negative. But remember, when calculating the principal value, ignore that minus and then work out the inverse sine of the positive value. So only when calculating the principal value, ignore the minus here, work out the inverse sine of the positive value. Okay. So in this case, if you work out the inverse sine of 1, you're going to get 90 degrees. That's a standard result. Sine 90 is 1. Okay, but you need to plot 90 where sine is negative. Okay. I don't like to plot the solutions on the same cast diagram. So for the second equation, let me draw a separate cast diagram just to make things clearer. Let's include some quadrants. Let's label them. So we need to plot 90 where sine is negative. So sine is positive in the first two quadrants. Sine is negative in the remaining quadrants, quadrants 3 and 4. And we plot our angles from the horizontal. So in quadrant 3, 90 from the horizontal is this line here. So from the horizontal, here's the line representing 90. And in quadrant 4, from the horizontal again, 90 from the horizontal, this line again here. Okay. Since all of these solutions are solutions to one equation, so the equation is cos 2x equals sine x, what I'm going to do is I'm going to name this solution x3. So this continues from the previous solution, which is x2. Okay, so x3 will be, as we want positive solutions for x, from the initial line, until we hit that line. So from the initial line in the anti-clockwise direction until we hit this line is 270 degrees. Okay? So that is the only solution that we have for the second equation. So we've got one solution for the second equation, two solutions from the first equation. All in all, we have three solutions for x. Okay? So that completes this example, and here are the steps involved. The operative thing to note is that if one of the angles in your trigonometric equation is 2 of an angle, so I have 2 of an x over here, think firstly about the double angle formulae, and that might help you solve your trigonometric equation concerned. Okay, so that's a good tip to note. Okay, so here are the steps involved. Let's try another example. So I think another example is in order. So let me continue on the reverse. So let me call this part B. Okay, so part B is, let's solve this equation. Sine 2x is equal to cos x. So again over here I've got 2 of an angle. I'm going to be using the double angle formulae. Okay, so if I go back to the double angle formulae, I'm obviously going to be using the one involving sine. So sine 2a, remember, is 2 sine a cos a. Okay, so here's step number 1. By using sine 2x, that's equal to 2 sine x cos x. Okay, so if I do the replacement in my equation in question, sine 2x is 2 sine x cos x, and that's equal to cos x on the right hand side. Okay, now from here on, guys, what I would say is do not cancel by cos x. You can't cancel by a variable quantity. Cos x is a variable quantity. You can't cancel by a variable quantity. What I would say is take the term to the left hand side. Okay, so if I take that term to the left hand side, 2 sine x cos x minus cos x is equal to 0. Okay, so cancelling by a variable is a no-no, so don't do that. Okay, so instead take it to one side, and what I'm going to do now is let me factorise. Let me take a common factor of cos x, giving me 2 sine x minus 1, that's equal to 0. Okay, and in this case I have two equations, so either cos x is equal to 0, let's call that equation number 1, or 2 sine x minus 1 is equal to 0, and if I rearrange, sine x is equal to half. So I'll name that equation 2. Okay, so just to repeat, everyone, don't be tempted to cancel by cos x, that's a no-no. Instead, take it to one side and factorise. Okay, so never cancel by a variable. Cos x is a variable. You can only cancel by constants. Okay, so in this case I have two equations to solve. So the next step, let's call this step number 2. Let me solve the first equation. Equation 1 reads cos x equals 0. Okay, now 0 I'm assuming positive, so when calculating the principal value it's the inverse cos of 0. Okay, and the inverse cos of 0 is a standard result. Okay, inverse cos of 0 should be 90 degrees. Okay, so that is your principal value for that equation. Okay, Now, in this case, we need to plot 90 degrees where cos is positive, so it's cast diagram time. So let me draw a cast diagram. Let's include some quadrants. Let's label the quadrants A, S, T and C. Okay? And we need to plot 90 where cos is positive, so cos is positive in the first and fourth quadrants. And 90 degrees, so when plotting it on our cast diagram, measure it from the horizontal. 90 degrees from the horizontal in quadrant 1 is this line here. 90 degrees from the horizontal in quadrant 4, represented by that line there. Okay, so I'll call the first solution x1. So taking my red pen, measuring the solutions from the initial line, 90 degrees from the initial line in the anti-clockwise direction, since we're calculating positive solutions. So the first solution is 90 degrees. Okay. Second solution, I'll name that x2. So from the initial line in the anti-clockwise direction until we strike that second line is 270 degrees. So all in all, we've got two solutions for equation 1, but don't forget we have another equation to solve, equation 2. So a new page, I think. Let's go to equation number 2. So equation number 2 is sine x is equal to half. Now, half on the right hand side is positive, so that gives us an indication where to plot our principal value. So we need to plot our angle where sine is positive, and x is the inverse sine of half. That's the standard result, 30 degrees. So that is our principal value. Okay. Now, I don't like to draw everything on one cast diagram, so let me use a separate one for the second equation. Let's include some quadrants. Let's label them A, S, T, C. So sine is positive in the first and second quadrants. So in the first quadrant, 30 degrees from the horizontal. Let's take a ruler, a rough representation, okay, of 30 degrees in quadrant 1, and 30 degrees from the horizontal in quadrant 2, again a rough representation. Here's 30 degrees in quadrant 2. Okay, again we're working out the angles x, and remember our range, we need to work out the solutions or the angles for x between 360 and 0 degrees inclusive. So looking at our cast diagram, the first solution, the first positive solution, is from the initial line in the anti-clockwise direction until we strike that first line. And in this case, let's calculate that. Now I've labelled, or I've named the last solution x2, and remember all of these solutions are solutions to one equation. So I'm going to continue from x2. I'm going to name this solution x3. x3 is going to be 30 degrees with the help of this cast diagram. And x4, so taking this red pen, from the initial line until we strike that second line, x4 will be the angle in the straight line, 180 minus 30 degrees, so that being 150 degrees. Okay, so we've got two solutions for equation 2 and two solutions for equation 1. All in all, we have 4 solutions. Okay, so here are the steps involved for with this example here. So this is part B, and sadly this ends this video also. So I hope you enjoyed this video. If you did enjoy it, a like would be much appreciated, and do plenty of practice questions. Okay, so there's good websites out there offering practice questions. There's good books also out there in which you can practice your double angle formulae, and I hope to see you soon. Thank you.